Greetings, everybody, and hello. My name is Kevin Kawchak. I'm the founder and CEO of Chemical Q Device. This is Tuesday, October 29th, 2024, for number 151 for monoclonal antibody bioprocess engineering advancements. And this is using conversational AI. So if you've tuned into some of these previous ones, these are large language models or large multimodal models, mostly focused on text with numerical data on this specific one. So I'm going to go through a lot of these as far as, in specific, the three different types of large language model speed ups advantages going anywhere from about 100 times to over 300 times. And then getting into some of the details with part A, B, and C, part A being reports, part B being tables with numerical data, and part C being reports with numerical data. So this focused on, in specific, 16 of the 2024 monoclonal antibody bioprocess papers, either that continuous bioprocess, so it's a continuous with a perfusion flow, or they already had some other types of AI advancements, and how can you make it better with conversational AI. So what's shown in the upper left-hand corner is a bioreactor. So you have dissolved oxygen, it stirs at some rate. And these types of things, they're continuously under improvement because a lot of the drugs have come off of patent, and they're called biosimilars for cancer. You see some for arthritis, and you also see it for COVID-19 vaccines as well. So it's just a very specific type of drug category that is very well produced. And even if you call this like a generic phase that we're in now, they've taken over the market share of the original patented drugs because they can sell at a lower rate, a lower cost. So on the right is basically the speed ups. So the first section here through 01 through 16 in average and sum, I took the 16 papers and I read the abstracts myself, represented by the number of words I generated, which is 86, up to about 112. Now, this took me considerable time. So 330 seconds, you see a 610 seconds for the next one. Now, the time it took large language models was significantly lower. So 20 seconds, and then you could see nothing over 60 seconds. And then the words are substantially higher than what I could do too. And this carries on from the previous paclitaxel biosynthesis breakthrough paper previously, where I said 10 times faster and 10 times as many words. So I'm counting it as an effective multiplier of about 110x on this specific section that you see, where I averaged, a lot lower words, and then the LLMs, more words, and I was a lot slower, and then the LLM's a lot faster. Now, the second speed up advantage here, shown in part A, is basically I asked ChatGPT 4.0 how long would it take the fastest human or optimal human to create a 250-word summary, and they said 55 minutes to do this specific prompt. Now, when I had the actual LLM, I believe it's the ChatGPT 4.0, it did it in 29 seconds and 850 words, 15 words. So it's an effective speed up multiplier of 371, okay? And the last speed up was shown, basically, I read the full Konoike et al. Paper, and then I answered the prompt as close as I could to answering to how the generative AI model answered the same prompt too. I was at 272 words. I actually have the example at the end of this, these slides to show you too. It was at 607 words. I was at 5276 to read the article and write, and it was at 35 seconds. So it's 330 times, when adjusting for the same number of words, faster. So, and also we're getting quality too. So ever since the May GPT 4.0 or ChatGPT 4.0 in this case, and, the June 3.5 Sonnet, and then also the July Llama models, so 3.1, 405B, and then the September 01 preview, we're getting the quality to also match the speed as well. Now, in this specific section here, I show how each section was done. So if I'm taking a single paper and generating a response that's represented by this first vertical bar, right? So parts A1, B1, C1, Gen AI reads a paper, and then you get the summaries, and then I combine them either into a 5 or 6 word summary. Now, the second part is basically I have a 5 or 6 paper summary, and then it goes and I give it to another LLM, with a prompt, and then it goes and solves the questions, the core questions in the paper. Now, the last one is basically an optimal human response. I asked ChatGPT 4.0, how long it takes to do this task, and then the answer is returned. Now, as far as the prompts themselves, I gave an example of the C2 because I really wanted this to highlight the paper. It was either that or the tables that did. So I said, create a report containing numerical data that cites authors' numerical values in quotations, along with large language model forecasted numerical values, not percent increases, regarding monoclonal antibody production improvements, citing authors' names for each of the 6 papers. Okay, so that's an example of basically in the previous prompt in C1, I get all the individual paper summaries as it relates to this specific task of machine learning with large language models. And in this case, I think it was reinforcement learning and Bayesian optimization. And then the paper goes into it in much more detail. There's 6 different machine learning methods that I focus on as far as how LLMs can improve monoanaclon MAB workflows. I included in the bottom right-hand section here another diagram. This is bevacizumab, so I believe this is for breast cancer. And there's just a whole host of different types of monoanaclon MAB workflows that were used, across this paper here. So the specific parts here, the earlier parts, what's shown here is basically the very first step of part A, where it just gets the paper summaries. So when I judge these based on conditions, what I'll get to here, is that you see in the progression here that the part B and part C, it didn't do as well because it's based on 5 or 6 other papers. So if it's missing one, I can't give it a high score, right? And one of them in part C was actually due to the context length of the O1 preview is not that large. It's like 8,000 or something like that tokens. So 1 or 2 of the papers were not at top caliber. Whereas, in these earlier parts, typically a single paper had a better chance of being, a higher score. So, and part B represents tables, and part C is tables with numerical data. Now, I included some of the conditions in the lower right-hand corner here. So condition 1, report results return in an order of paper summaries with authors' names. In other words, however I presented the data, it didn't mix up the order of the authors. Now, number 2, report is complete. Number 3, report is detailed. And number 4, report is convincing. So it's a combination of the factual correctness, and I have to go through these and look in the original papers. And these words, they get up to, you see 772 on the left one, the O1 preview, and then also with this one, 430 words, right? So they're getting up there on the words, but I have to read, especially the ones that I put into the manuscripts. Now, on the left is basically a diagram of what goes on in order to get the antibodies, right? So you see the clone picking at the end, but typically this is with some type of Chinese hamster ovary, immunization, and then myeloma cells, electrofusion. And, so basically this is considered upstream, like the actual processing to get it, analogous to like a chemical synthesis. And then the downstream is going to be more so like with purification. Okay, so these 2 different parts that I picked, the O1 preview, and this is a single paper summary of paper 4 by Okamura, K et al. In this year. All the papers were 2024s. And in specific, it did a really good job. So as far as the level of detail, I did read this one, and this was 10 out of 10 that I gave this specific one. Again, the O1 preview tended to be a lot more detailed, lengthier, but a lot of times, deserving of it. Now, the 3.1 405B, you see, is significantly smaller at 430 words. And I gave it a 9.5 out of 10. And it was typically O1 preview number one, and then followed by ChatGPT 4.0, sometimes tied with 405 billion with the Llama 3.1. And then usually the Sonnet just did not do well in this study as a whole, although they did announce a new model last week. That was after I collected all the data. Okay. And then, so I thought that this turned out, especially for the ChatGPT 4.0. So this is the whole crux of where I believe everything's going. So a lot of times you'll use like a mechanistic model or more deterministic model in AI to get the same answer, every time you get the same input. Now, large language models and generative AI in general are not set up like that. They're more like you have vast amounts of data. You have different types of context going on. You have numbers, you have text, it's in tabular form, it's in all these different things. And it excels in taking all of this and providing an answer in English as far as what's going on with a whole process, as opposed to individual portions of it, okay? And you really just, like, for instance, with the ChatGPT 4.0, it gave the original numerical data. So I go through and check all these, and I believe all these were correct, this whole column, original numerical data. So just imagine being this, collecting it from different parts of the process in a semi-automated manner where it's going to take a little time to run, but get all of the individual types of machine learning data and just other data from sensors and have a new contextual understanding of this whole process and this as a new utility, as opposed to other, more individualized outputs going on. So again, I went through all of these, and again, it returned these in order. So Pybus et al., Liang et al., Knoike et al., Sarkis et al., Lucas et al., and it split it up pretty evenly. You see some Sarkis had 1, 2, 3, 4, 5, and Lucas only had 3. But that's a function of how much original data was in the paper. But this in particular on the left-hand side is where I see the industry going, because, as opposed to just saying oh, we can only study this specific aspect. And as well as I do with machine learning, that a lot of it is just more rigid and it's just designed to give the same answer for the same inputs. But what's going on now is take all of this information and then get a solution within minutes, and then consult with a human AI team, and then say, okay, this whole process that LLMs or ChatGPT or 3.1 Llama is finding, it is actually this, and this specific thing would help. So that's how I would look at it. I wouldn't look at it like it's going to replace any of the necessary parts of machine learning, but it's another utility that says it has a brain on its own. When I pointed at new data, like a document retrieval or RAG, retrieval augmented generation, now we have a new utility and a new tool in our tool belt to look at the whole process. Okay. So again, pretty happy with the ChatGPT 4.0 table. I gave it a 9 out of 10. And then the one on the right, it had just a couple NAs, something like virus inactivation pH. I don't see that changing. So a 6.5 pH, I don't see, if that's just a standard workflow parameter. But anyways, that was one of the few NAs or not applicables for ChatGPT. Now, the 3.5 Sonnet did not do as well. I wanted to give a good representation, even though this model was tested before, like I said, they came out with their new models. And, so we see in specific with this, the glaring thing was this not specified, this whole single column here. So I wasn't sure, it's probably lack of contextual awareness, between all these summaries that it was given to him. In this case, it was six single paper summaries. And it's dissimilar and disparate information between them. So it's not an easy task at all. And it actually represented, probably overrepresented, Ling et al. And that's looking like something like 10 times. And some of these other ones, a lot fewer, like the Sarkis et al., something like 4. However, besides these Liangs, and this probably goes back to the original paper summary, the rest of it, actually, a lot of the author values and the LLM forecasted values seem to make sense. Now, this was the crux of the whole manuscript. So this is part C, and I chose O1 preview, which is basically it gets all of this. It's a 6-paper summary, and actually part B was a 5-paper summary. So this is a 6-paper summary, and then you see here Thacker et al., Kunzelman et al., Quat et al., and it goes one after another in a systematic fashion: Eslami et al., Agarwal et al., and Wang et al. And most of these it did just fine, but one of them, the Quat et al., it actually got the original time that it did it, it wouldn't let me submit it because it's like 70,000 words. And I kept trying to cut it down to like an appropriate amount. And I basically was wound up with like the abstract to introduction and 4 sections of this abbreviated paper. And I think it caused an error, basically, because I kept reducing the amount and it was looking at something earlier. So that one didn't. And there's some things as far as like, if it'll be like a mu instead of a q that it's supposed to be at, but not as big of a deal. But so most of them did a pretty good job. And again, you could look through the manuscript too, because I have to do this and I'll copy and paste. And most of the times this text is right in the original paper. So when it says it gives a new forecasted increase from 55 to 80 hours of continuous steady state operation, that's an improvement that the LLM thinks that it could do once it's, on the line. And then I wanted to include this. So I did triplicates of each of the original A1, B1, C1, which are single paper summaries. And basically the averages, they make sense between the words and the times. So we have 450 words, 19 seconds, 480 words, 27. So they're kind of like equilibrated pretty well. Now the standard deviations were higher. So if I did ChatGPT 4.0 on a single paper for the optimal human time, the standard deviation for the words was 19. And then the words for the, across the 4 different models was higher at 160, about 10x. But that's as to be anticipated. This software is running in different parts of the country on different inferencing hardware too. So, and the software itself is of different sizes and those types of things. So it's good to see the relatively low standard deviation for the paper 5 for the part OH on that specific one. I also wanted to show my response. So I took a paper and I read it. And then later I came back and then I provided this, my best summary at 272 words. And that whole process, 52.76 seconds, which is like, the Gen AI models are getting typically under a minute. And this is the last one as far as the speed advantage at 336 times faster when adjusted for same words for the large language model. And that's in the appendix. Now, wrapping all this stuff up as far as where this came and how it came to looking at using LLMs as production. Now, these first 2 studies that I did represented here, they're large language models and they're direct prompts. So they're on cancer drug synthesis like paclitaxel, methotrexate, like, design your better, faster, cheaper way of synthesizing methotrexate, or the paclitaxel start with, hydrogen gas, nitrogen gas, oxygen gas, some very simple starting materials and carbon dioxide. So it was interesting to see the responses to it. And again, these are recorded. Now, the next 2, I bumped it up. Now, there is an advantage to doing machine learning with large language models in training phase, okay? But this is typically a lot less accessible. You're trying to get to some type of an inference model so that you can run on a semi-continuous line, like a production line. However, when you use document retrieval, like in these specific ones, it points to the specific data. So it's a lot less likely to get any of the ills of large language models, such as hallucinations. So for these 2, this third one, I used organic syntheses papers. I used 3 of them. And for ChatGPT 4.0, it was able to get high performance, whether it was looking at 1 or 3 papers all at the same time. And this next one with JAX and Nature Communications, this one was primarily focused on purity and yield, and then speed and cost at the end. And I would ask it specific reaction questions in the papers. And I judged it similar to actually this most recent manuscript. And it did pretty good, like, so was it was it complete? Did it provide quotations? And just so you know, the LLMs are a lot better at quotations than other things such like page numbers, line numbers, because those can vary from papers to papers. And your interpretation of it might not be its interpretation. So I always, when I can, I try to ask for quotes of text where it got it from. So these two did well, and especially because of the document retrieval, being pointed to this specific information. Now that launched these 5 manuscripts. So the first one, LMM chemical research, that stands for large multimodal model. And I put it through the ringer. So the first 5 prompts were all image based. So this is 1D, 2D NMR. This is mass spectrum, or at least one of those. And, so I really tried to, like, whatever I could find, or I find reactions that were, in with organic structures, clip that, and then, see what it would do. So that one was like, a mini breakthrough because it showed the broad utility, and especially with text, and text is still king. And I can do things with images as far as like pre-training or fine-tuning on images, but just as a whole, I really see the breakthroughs with the processing data, numerical data, and especially like getting to a different conclusion that you couldn't before because of the, big data, and also the contextual awareness of the model. Now, the next 2 models, or the next 2 papers here, or manuscripts, are basically this LMM spectrometric determination. Is I'd find all of these, problems regarding, solve this, and it was a UCLA web spectra problem, and it had 4 different spectra, and it gave you the molecular formula C9H7N. And in that specific case, I gave it to 3 OpenAI models, and they all solved it. And the answer was quinoline. And there was other things in there too, but if the complexity get too high, it was something it didn't do as well at. Now, the next one I had approached initially, I had 13 chemical spectra. This was a UC Irvine final exam problem. So this high dimensional complex spectrometric data analysis. And on that specific one, the LLMs were not able to, use the plain old images and convert it into tabular data and then convert it into an answer. I did have to provide it the tabulated data, which is still very complicated. And actually, it was 3.5 Sonnet that came up with this answer called ethyl ester ibuprofen. So it's an ethylated ibuprofen on the ester portion. And then I published that one. And then right after that, I tested it again with O1 preview, and it got the same solution. So I think that's right. It's an organic unknown problem. Again, I took that course a couple times in college and did very well in it. But that was harder than my final exam question. Now, the last 2, which brings us up to this current manuscript with the paclitaxel biosynthesis, is basically, I called that a breakthrough because it's basically I had 10, 2024 paclitaxel biosynthesis papers. I had that going into another 10-page summary. And then I had that going from anywhere from historical emerging solutions of retro biosynthesis pathways. It's very interesting, a lot of work, especially, in the supplementary too. And then also with, cellular engineering, basically what it thinks in top 10 new research areas and top 10 challenges in the area. So I would definitely check that out. And again, some of the speed advantages started with that too, with, basically 10 times faster and 10 times as many words. Okay, so and then I talked about the MAB workflows on this specific one. And basically that whole spiel I gave is also lined up in section 6 in the specific manuscript. It's up on ChemArchive. I would definitely check it out. And it goes through, those 9 works in specific, how it got to this point today that we're looking at, basically with LLMs and getting to production data and, new utility and those types of things in a more conversational way, but also high performance in, vast amounts of data too. Okay. So This has been Tuesday, October 29th, 2024. Again, my name is Kevin Kotchak. I'm the founder CEO of Chemical Q Device for 151 monoclonal antibodies. And again, all of these are up online. And again, I'm continually moving with this. So I'm going in that direction of more and more production data, probably doing simulations, so real lifetime simulations, and then have this type of software capture that, every so often frequently, and then using a human to, go to the next steps or what the next step should be. Okay. So thanks everybody for tuning in. Have a good rest of the night and have a productive rest of the week. Take care.